All right, guys, let's finish off section 8.3, which will be the last stuff we'll go over before our next big quiz, and obviously just check Schoology for when that's going to be and the date. And it brings us to a kind of a weird topic. We were just finishing recently talking about finding the sum of a geometric series, and I'm going to pose this question: can there be a sum to an infinite series? So a series that goes on forever, you're always adding more and more numbers. Is there any possible way to find a sum to that type of series? Well, let's start with arithmetic. If you're always adding, in this case 4, to the next term, the terms are getting bigger and bigger and bigger. And if it goes on forever, I think we can all kind of look at that and say, well, there's no possible way. There's no sum to this. Even if the numbers were getting smaller because you were adding on a negative, might seem like, well, that's 35, 45, 50, and maybe if you keep, but the next term is going to be 0, and then -5, and -10, and -15, and -20, and it's going to keep going on to the big negatives forever. So there's no real way to add those numbers together. It's just going to be a huge, huge, huge negative number. So again, that would also be no sum. So I think you can pretty safely say that if it's arithmetic, there's no way to find the sum to an infinite arithmetic series. What about geometric? Well, here we got one that's going up by a ratio of 3, and here we have one that's going down actually by a ratio of 1/2. Well, obviously this one's exploding pretty quickly. The next term's going to be in the hundreds and the thousands. Start adding those terms together. If you go on forever, again, no sum. But if you look at this next one, and you see each term's getting smaller and smaller because you're multiplying by 1/2, you could say this is 36, and then plus 6 is 42, plus 5 is 45, and then you're going to add on 1.5, and then half of that, half of that, half of that. And it seems as if you're adding on smaller and smaller numbers, but you're always adding more. The question is, does it add up to something? And it kind of goes back to that same question we've dealt with before. Like if I walk halfway to the door, how far have I walked? If I walk halfway again, how far have I walked? And if I keep walking halfway and halfway and halfway to the door, and I started 20 feet away, do I actually cover the full 20? Or am I always just a little bit short because I'm walking halfway of something, even if it's so small? It's one of those weird concepts in math. And believe it or not, if the ratio, and either positive or negative, if the ratio is less than 1, okay? So if the ratio is less than 1, so you have a fraction, so to speak, a fraction less than 1, as your ratio, there is a sum. And some of you may protest this. You're like, well, no, because you're always adding on the next term and the next term, but it turns out that you're adding on such a small amount that it actually ends up equaling something. Kind of like if I kept walking halfway to the door, would I actually cover the full 20 feet or not? So mathematically, maybe how I could justify this to you is if you look at the geometric sum formula, this part right here becomes the key part. For example, on this one that we were working on, the ratio was 1/2. And if you started taking 1/2 and raising it to a bigger and bigger power, even if you did it, say, to the 10th power, then the 100th power, then the 1000th power, and certainly to the 1000th power is not really infinity. Okay, again, we're talking about infinite. So if it went on forever, you try with your calculator. What eventually is going to happen is this whole term, if you start doing 1/2 to the, say, the 10th power, 1/2 to the 100th power, 1/2 to the whatever, 1/1,000,000th power. Just do it on your calculator and you'll see that eventually the calculator is just going to give up and it's going to say 0, okay, because it's so infinitesimally small. So this whole term drops out if the n gets big enough. And if the n is big enough, when we're talking about infinite, obviously that's pretty big. So what happens for an infinite, and it has to be geometric, okay, we already talked about arithmetic, but also with a ratio less than 1, there is a sum, and you don't even have to put an n down there because it's just the total sum, the infinite sum. If you want to put an infinity in there, you can. Just ends up being this first term, okay, because this term dropped out, so it's just the first term over 1 minus the ratio. It actually is way easier to use than the geometric series sum formula, but you can only use it when you're finding the sum of an infinite, geometric, and the ratio has to be less than 1. So it is your fifth formula, fifth of 5, that you'll use to find the sum, but you'll only use it in very specific cases when it's infinite, it's geometric, and the ratio is less than 1. So you're going to get questions on homeworks and quizzes. We'll say, find the sum, and then they'll start putting in if possible for the following series. Now notice that all 4 of them are infinite, so very good chance that there isn't going to be a sum because it's infinite. This looks like you are multiplying by 4, ratio of, let's see, 2 times 4 is 8, 8 times 4 is 32, 32. Okay, so it is geometric, but the ratio here is 4, so you get to write down no sum right away. This one looks like, let's see, you're adding 6, adding 6, adding 6. Okay, anytime you're adding, that's an arithmetic, and there's no chance for a sum of an arithmetic if it's infinite. So again, it's kind of nice because you get to write down no sum a lot if it's infinite. Now this next one, kind of like the one we were working on with our example, has a ratio that equals what? 1/3. You're multiplying by 1/3 each time. So that means the next consecutive terms are getting smaller and smaller and smaller until the point where they basically don't have any value and they're not adding anything. So watch how easy this is. You can say the total sum is the first term 27 over 1 minus the ratio. Little bit of fraction work here, but I don't want anybody to freak out. It's not nearly as hard as it seems. You can take 27, this is going to be divided by 2/3. So that's 27 times 3 over 2. Remember, when you divide by a fraction, it's the same as multiplying by the reciprocal. And what you're going to have is what? 20, that's 81 halves. So 81 halves, or 40 and a half. Believe it or not, this series, infinite, will add up to exactly 40 and a half, 81 halves. And you can kind of see that it's getting there. 27 plus 9 is 36, 36 plus 3 is 39, plus 40. The next one would be 40 and a third, and then you add on a sixth, and so on and so on. So believe it or not, those numbers will add up to, even if you kept adding on forever, they will add up to 81 halves or 40 and a half. This one, the last example here, you can see it's getting smaller, so there's definitely a chance. Ratio here is -1/2. You're multiplying by -1/2 each time. So if you want to find the sum, total sum, you could say it's 16, the first term, over 1 minus. Be careful here, you got a negative ratio, so it's going to be 1 minus, so 1 plus 1/2, and minus the negative, 1 minus the negative. So that's 16 over 3 halves, which will be 16 times 2/3, or 32 thirds. I like to always put these in mixed number notation just so you can kind of see what it is. That's the same as 10 and 2/3. And can you convince yourself that that might be right? Well, 16 minus 8 is 8. 8 plus 4 is 12. 12 minus 2 is 10. And you can start seeing how it's narrowing in kind of on a number somewhere around 10. And you can maybe convince yourself that 10 and 2/3 is exactly the answer. So kind of a last little bit to section 8.3. Special formula to find the sum of an infinite series, but remember it only works if the infinite series is, well, first of all, it can't have a ratio bigger than 1 if it's geometric. If it's arithmetic, just throw it out, no possible sum. The only types that do are infinite, geometric, where the ratio is less than 1. And when I say that, I mean whether it's negative or positive, it's less than 1. That's why we have it in absolute value bars here. All right, that does it for our study of sequences and series. Expect a quiz soon on this material. Obviously, some of it's calculator-based, especially section 8.3, but a lot of it is just kind of playing with numbers and figuring out patterns of numbers and recognizing whether it's arithmetic or geometric, and going from there. So good luck.